Enterprise AI applications are designed to process highly sensitive business logic. The friction points emerge when we pair that logic with a conversational interface. Chatbots feel informal, which inadvertently encourages users to drop their guard and type out proprietary details in plain text. This means that without the user explicitly realizing the risk, sensitive data diffuses continuously into the system architecture. To map the risk, let's look at standard AI architecture. A user node sends payloads to the application server. The first exposure is the outbound path, forwarding raw prompts to an LLM. The second is the inbound path, writing chat history to database storage. Securing an enterprise application requires discarding the idea of a static perimeter. A secure firewall is useless if the system itself is designed to hand proprietary data over to an external API. Security here demands a workflow design philosophy. The strategy is internal exposure reduction. Data must be actively minimized and sanitized at every single internal transition point within the architecture, long before it reaches an external boundary. To operate safely, an enterprise system must mathematically guarantee two things. Sensitive data is never leaked to third-party language models, and it is never left exposed in the underlying databases. The secure workflow begins the moment a user hits send. We trace the prompt as it leaves the client device and arrives at the application server. Sending raw personal information over the network to an LLM immediately expands the system's risk footprint. In most enterprise environments, it directly violates strict data compliance protocols. We mitigate this with the first architectural defense, a message cleansing component. This system sits right in the middle of the pipeline, operating entirely within the secure local bounds of the application server. The operational mechanism is an active scan. The component inspects the incoming text payload locally, intercepting the data before any external network calls are allowed to execute. The cleansing component is programmed to detect specific entity classifications. It actively looks for string patterns that match names, dates, specific organizations, and contact information. Let's look at a simulated text payload block. Schedule a review for John Doe at Acme Corp regarding john@email.com. During the detection phase, the system identifies and flags the targeted entity classifications. Next, the algorithm strips those sensitive entities completely out of the string. Finally, the redaction process injects standardized placeholders into the gaps. This newly transformed payload is now completely sanitized of personal data. Crucially, however, it retains its exact original syntactic structure. This redacted payload actually travels over the outbound network path to the third-party LLM API. This approach allows the LLM to receive the exact grammatical context it needs to generate a highly accurate response, but it accomplishes that task without requiring access to a single proprietary detail. Because this redaction occurred entirely pre-flight, zero private information ever crossed the enterprise network boundary. Programmatic preprocessing functions as an inference firewall. It isolates proprietary data inside the enterprise perimeter while fully maintaining the utility of the AI application. We can now shift the architectural focus to the return path. The LLM processes the sanitized prompt and generates a response, which arrives back at the enterprise application server. The server merges this response with the user's prompt history. This creates a stateful chat log, which now needs to be queued for persistent storage. Naive data pipelines take this raw, clear text message content and write it directly to a database. Relying solely on standard database-level security is a severe vulnerability. If an attacker breaches the database layer, or if an internal user gains improper access, the entire historical chat record is immediately readable. The structural solution is to intercept the data payload at the application layer before the database write operation ever executes. At this transition point, we deploy a specific cryptographic mechanism, symmetric encryption. Symmetric encryption relies on a single, unified secret key. The exact same mathematical key is used to execute both the locking and unlocking algorithms. This is the optimal engineering choice for securing data at rest at the application layer. It offers distinct, low-latency performance benefits. When you are building a chat application, you need to process continuous text streams in real time. Symmetric encryption provides the necessary speed. We can visualize the clear text chat log waiting in the application server's memory queue. The application server applies the symmetric key to the chat log data. This triggers a state change. The readable text is mathematically transformed into an unreadable ciphertext string. This introduces a logistical formatting challenge. Cryptographic transformations output raw byte arrays. Standard database text fields cannot reliably store raw binary data without risking corruption. To fix this, the system applies an encoding step. It encodes the ciphertext into a stable format, like base 64. This guarantees the encrypted data can be safely written to standard database tables. When a user opens their chat history, the process runs in reverse. The client sends a read request, pulling the encoded ciphertext from the database back up to the server. The application server intercepts that read payload, decodes it, and applies the exact same symmetric key to decrypt the data back into clear text, which is then rendered on the front end. By shifting cryptographic operations to the application layer, the system neutralizes database vulnerabilities. All stored records remain mathematically protected, even if the underlying storage infrastructure is compromised. When we map the complete end-to-end data pipeline, the structural integrity of the architecture becomes clear. We establish the first perimeter defense by validating the incoming user request via token-based access. We establish the outbound defense by programmatically redacting PII, creating an inference firewall before any third-party model call occurs. And we establish the inbound defense by symmetrically encrypting the payload at the application layer before authorizing persistent storage. Combining token validation, redaction, and encryption effectively shrinks the application's overall exposure surface to near zero. The logic of the system is secure. The next necessary phase in the development lifecycle is deployment. In the next video, we will cover how to package and serve these front-end and back-end components in unison. True enterprise AI security requires systematically engineering the workflow to eliminate data exposure at every single transitional step.